All right, so our next talk follows on very closely. This is a comparison of VR locomotion systems, including the Ecto Boots, presented by Jim O'Neill, who's the group supervisor for the Immersive Training and Software Solutions group at APL. Darrell Diaz, who is a fourth-year PhD student at Clemson University, focusing on research within augmented and virtual reality systems. And Luke Vernon, who is a rising junior at the University of Maryland, College Park, majoring in computer science. Jim?
Thanks, Ari. So like Ari said, I'm the group supervisor for the Immersive Training and Software Solutions group. We do a lot of training solutions for the DoD writ large. And how this experiment came together and came to be an intern project really started with the acquisition of the Ecto Boots last year. We then bought the Cyberith Virtualizer 2 from an Austrian company, Cyberith, just earlier this year, as well as the Infinideck. So we were lucky enough to get some IRAD money, independent research and development, in order to pass it along to these gentlemen in order to do an experiment that really targeted that demographic for younger sailors or younger people really entering the military. So over to Darrell and Luke.
All right, we'll be presenting the results of our experiment towards better travel, comparison of VR locomotion systems in urgent and important tasking. So for some background information, first to go over the pre-existing methods of locomotion in VR. We have teleportation, which is an instantaneous movement from one point to another. We have smooth locomotion, which is more like a traditional video game, where you use a joystick or a thumb pad to move the character smoothly. We have dashing, which is like a slower version of teleportation, usually accompanied with an animation. And then, last but not least, we have real walking, which is the most immersive, but has the downside that the physical space has to be as large as the virtual space. Today, we're going to be talking about and evaluating some new methods of locomotion, including omnidirectional treadmills and treadmill boots, the Ecto Boots, as you just saw. And we're going to be looking at the trade-offs between speed and accuracy for the different tasks that we have. We designed the task to fit between the 4 different quadrants of the Eisenhower matrix, which is like an important versus urgent matrix, and we have one task in each quadrant. So for the locomotion systems we'll be looking at today, we have the Cyberith Virtualizer Elite 2, where participants put slippery shoes on and they slide on a sliding, rotating, and tilting platform that allows them to walk as if they're sort of roller skating. Then we have the Infinideck, which is an omnidirectional treadmill. That means it's just like a treadmill, except it moves in all 360 degrees. Next, we have the Ecto Boots, which I'm sure we're all familiar with. They're basically like omnidirectional treadmills under your feet, so whenever you step, they move you seamlessly back to the center. And last but not least, as our control, we have real walking, a combination of real walking and teleportation. The teleportation is needed because, of course, the virtual space is much larger than the physical space. So for this study, we aim to compare and analyze these different systems for different tasks. We asked questions such as which system would allow for the fastest task completion, highest usability or ease of use for the user experience, least simulator sickness, and which one the participants generally preferred the most. We hypothesized that the systems with the most restrictive movement, and by that we mean the systems that sort of hold you in place, like with the virtualizer, the hip ring, and the Infinideck with the ring that you hold onto. Those systems would have the fastest completion times. We also predict that there wouldn't be any difference in usability or ease of use with the different systems. And we also predict that the systems with limited movement would have a higher rate of simulator sickness. And last but not least, we predict that the real walking condition would be the most preferred system because it is the most natural. So now for our methodology. To develop the tasks in the environment, we use the Unity game engine, and we ran on Steam VR. We use the Vive Pro 2 headset with the Vive Wireless. And to do our data analysis, we used R and RStudio. Here are the specs for the PCs that we used for each system, in case you're curious. It's important to note that we don't think that the difference in specs made any difference in the experiment. It didn't have any relevance. Now for our experimental design, we targeted the demographic of new US military members, so early 20s. We had a within-subject design, so each participant participated in all 4 systems and did all 4 tasks on each. And so we followed the Latin square design method, where each participants were staggered, so each participant started with a different system, and they rotated through all of them in the same order. This helps us to eliminate learning effects, where participants will just naturally have a bias towards the very first system that they try. And the order of tasks that they do in each system is also randomized to, again, eliminate that bias. So after each system that the participant tries, they'll fill out a series of questionnaires. We have a simulator sickness questionnaire, which is a 5-point Likert scale, 1 to 5, that asks questions such as, I think I would like to use the system frequently. We have a system usability survey, which measures the participant's ease of use. We have a system preference survey, where there are 12 questions, and they select which system they would prefer to most when different actions are required, such as reaching high, reaching low, walking fast, et cetera. And we had some free response questions at the end. So now to talk about our tasks. They worked in an environment developed by APL for the Navy, and we've shown the tasks here without the background. So the first task is a task where the participants have to walk around, bend down to the floor, and pick up screws. The next task is picking up a nitrogen tank that's fallen onto the floor. So again, they have to bend down to the floor, pull something up, and then twist a cap on the top. And the next two tasks are the bucket task, where the participants have to pick up a bucket, maneuver around some objects that you can't see here, and place the bucket down in another place. And then last but not least, we have the power supply task, where participants have to pick up a power supply, move in a relatively straightforward direction, and place it back down. Another difference between these two tasks is that there are verbal instructions given to the participants in the experiment. And in the bucket task, the verbal instructions say that it's not a very urgent task, and the participants can be as slow and leisurely as they like. Whereas with the power supply task, they're instructed to move as quickly as reasonably possible because it is very urgent. So for a procedure, before each participant did the experiment, we gave them a brief safety and procedures brief. And they also filled out a pre-survey where we collected demographics like gender and age. And then in each system, again, because of the Latin square design method, each participant had a random starting first station. And if it was their first ever station that they did, we had them complete a short demo where they had to pick up an object, turn around, walk a few paces, and put it back down. This was just to get the participants used to the system and how to pick up objects using the trigger and so on and so forth. And then once they get out of the system, they complete the questionnaires that we discussed earlier. And then after they've finished all 4 systems, they fill out the post surveys, which is a system preference and free response. So now on to Daryl to talk about our results.
Awesome. All right, now that Luke has given you guys an understanding of our methodology and why we chose to do what we did, I'll go into the results. Okay, so as a quick refresh, for all the data we're going to show to you guys, we're using bar graphs, and it has statistical things on the bar graph that some of you may have not seen in a very long time, so we're just going to do a quick refresh. The capital I, or the barbell on the bar graph, represents the standard error, or in other words, the variability amongst data points, one standard deviation from the mean. Right below that, you'll see the p-values. Not only do we give the exact p-value, but also this is the probability of how confident we are that our data was not due to randomness. So in other words, 3 stars would represent that we're 99.9% confident that our data is not due to some random effect. 2 stars would be 99%, and 1 star 95%. In order to get these p-values, we have to compare the groups, and so therefore, we use the real walking system within our system comparison group, and then the bucket task within our task comparison group. And you'll always see this, the real walking or the bucket task, being the first item within the bar graph. So as a quick overview, our experiment took about an hour and a half to complete, given it 20 minutes per system. We had 12 APL interns, more specifically from the FPS group, and we had a perfect split of 6 male and 6 female with an average age of 21 years old. We utilized the Buildmer package within RStudio, which compares different models based on criteria and gives us the best predictive model. Most times than not, Buildmer suggested that we use a linear mixed effects regression model, and this was perfect because it considers differences from participant to participant, but also can make predictions based on missing or imbalanced data, which we had, and we'll talk a little bit more about further. And there also has to be a post hoc analysis done, which the post hoc analysis that were done for these models was an ANOVA with a Walds-D t-test. So one of our first measurements was completion time. In other words, how long it took participants to complete each task. Just a quick note, we'll only be showing main effects. We did have some interactions effects, but for the sake of time, we're just going to cover the main effects. In terms of our main effects, we had a main effect of task type and system type. More specifically, when it came to locomotion systems, the Cyberith was statistically significantly different from real walking in terms of taking longer to complete tasks. When it came to tasks, we saw that the nitrogen tank task and power supply task were statistically different compared to the bucket task. Given that they were statistically different, they were a lot quicker to complete. When it came to hand movement, we took the controller position from frame to frame, and we gathered a distance. We aggregated that distance for each participant, and on this measurement, we found that there was a main effect of task type and system type. When it came to the systems, we found that the Cyberith and the Infinidec were statistically different than real walking. So in other words, participants moved their heads less when compared to real walking. And on tasks, we found that the nitrogen tank task and the power supply task were, again, statistically different, meaning that participants moved their head a lot less within these tasks. When it came to head movement, just like the controllers, we took the head-mounted display and we got the distance from frame to frame, and we aggregated this for each participant. And what we found was there was a main effect of task type and system type. In terms of system type, the Ecto Boots was statistically significant compared to real walking, meaning that participants had to move their head more within the Ecto Boot system. And when it came to tasks, we found that the nitrogen tank task and power supply task, participants had to move their head a lot less compared to the bucket task. When it came to head movement, again, very similar to distance, we also took rotation or degrees. So for every frame, we looked at the degrees moved. And so we totaled this only on the X and Z direction. And so we totaled this for each participant, and we found that there was a main effect of task type, more specifically that the nitrogen tank task, the pickup screws task, and the power supply task were statistically significant when compared to the bucket task. And so now we discuss our results from the system usability survey. So this, we actually use a general linear regression model compared to the linear mixed effects regression model. And so for this, we found that the Cyberith, Ecto, and Infinidec were statistically significant compared to real walk-in. In other words, meaning that usability was higher for the Ecto Boots and lower for the Cyberith and Infinidec. When it came to simulator sickness, in other words, we had participants fill out the SSQ, Simulator Sickness Questionnaire. We found that participants got more sick, the Infinidec was statistically different than real walk-in. In other words, participants got more sick when they were in the Infinidec. When it came to system preference, as Luke mentioned earlier, we had 12 motions that we asked participants which system would they prefer using, and these were just some of the totals. It was interesting to see that when it came to reaching, bending, or crouching, participants rarely preferred the systems where there was a ring around them. And also a note here, again, the Ecto Boots, like Brad mentioned, we only had 5 participants, therefore we had to take a weighted average in terms of out of 5 participants, how many of them picked the Ecto Boots, and then for the other systems, since all participants got to experience those systems, we did it out of 12. Therefore, given the weighted average, we did a one-way ANOVA on these 12 parameters, and we found that there was a main effect. We found that there was a statistical difference with the Cyberith and the Infinidec. Therefore, participants significantly did not prefer these systems overall, just on our 12 parameters, when compared to real walking. Again, with the free response, this was what our participants told us, and we found that there was pros and cons of each system. Some pros for the Infinidec was that it was very realistic in terms of walking, and it felt like natural jogging, but it was difficult to move in certain directions and also required high effort. For the Ecto Boots, participants felt secure, and they didn't even notice that they were moving, but they also mentioned that the boots were heavy and they felt like they were walking slowly. When it came to real walking and teleportation, participants said that it was the easiest to use and least fatiguing, but also that after teleportation, it was hard for them to reorient, and sometimes they broke immersion. When it came to the Cyberith virtualizer, participants felt like it was an easy setup and they didn't feel like they were being pushed, but they also mentioned that it was slippery and sometimes the floor would be below the platform. And I'll explain a little bit more about that later. So going back to our conclusions, what we found was that task type usually had a main effect, meaning that the tasks that we chose within the Eisenhower matrix, again, we came up with these tasks, but we used the Eisenhower matrix as reference. The tasks that we chose were good measurements for evaluating these systems. And something to note, although that real walking was significantly preferred, the Ecto Boots was the only system to score an excellent on the system usability survey, which the other ones, real walking scored good, and the Cyberith and Infinidec scored okay. Because the system usability survey has its own scale. It's not, 90 to 100 is an A. It has its own scale, so we took that into account. So going back to our original hypotheses, Hypothesis 1 stated that the locomotion systems with restricted movement will have the fastest completion time. We reject this hypothesis. It was actually the opposite. Hypothesis 2, there will be no difference in the usability of locomotion systems. We also reject this hypothesis as the Ecto Boots and real walking had a higher usability, had a statistically significant difference in terms of usability. And for hypothesis 3, the locomotion systems with limited movement will have higher simulator sickness. We reject this hypothesis as well, but it was a gray area because the Infinidec, in other words, the ring systems, the Infinidec did have higher simulator sickness, but the Cyberith did not statistically. And for hypothesis 4, that the real walking condition would be the most preferred system to use. We accept this hypothesis as the data showed that this was true. So again, these systems aren't perfect, and so we had a little hiccup when it came to our experiment with the Ecto Boots. Like Brad mentioned, we had a hardware failure within our first group, but with the great customer service that they got on the phone on the drop of a dime, and David Garber, they were able to go back and fix the boots before our experiment finished, and we were able to get a total of 5 participants ran where it could have just been 1. With the Infinidec, we had some abrupt stops and calibration issues. We tried to work with their support team, but unfortunately, we were not able to get that resolved, and they weren't sure why we were having those issues either. When it came to real walking or teleportation, sometimes one controller would stop working, therefore made it really hard to teleport and grab an object. You had to do it all with one controller, and so therefore sometimes that, like they said, broke immersion and was just a bad experience to have. And with the chaperone grid, sometimes participants would unconsciously walk through the chaperone grid, and of course there was objects outside of that boundary. And this was usually for participants who'd never been in VR before, but sometimes it's very easy to walk through, so that was one of our limitations as well, which again breaks immersion. We also had some tracking loss across all systems in terms of having gray flashes within the headset, which this can induce a little bit more cyber sickness, but also is just not for a good user experience. Again, there's some limitations to each system. When it came to the Cyberith, as you can see, sometimes when participants had to reach down, for example, the picking up screw task, they would have to reach below the actual system. As you can see in the middle there, with the Infinidec, sometimes participants would have to walk off of the treadmill because of the calibration. And also when they would try to sometimes bend down to pick up something, it was a little jittery to stop them. For the Ecto Boots, sometimes participants, when they were walking, if they did not stop with their feet perfectly parallel. I guess this isn't always the case, but in some cases when participants did not stop with their feet parallel and with their feet like this, sometimes it would roll them back to the point where they would almost be doing a split. Some limitations are on our end, like Luke mentioned earlier. We did have some order effects in terms of what system participants were in after the previous one. And we also had some learning effects given that we expected participants to complete tasks a little easier and a little faster as they went along through this experiment. Like he mentioned though, we tried to mitigate this with randomizing the tasks and also doing the Latin square design. We only tested young participants, so we don't know if these results will propagate up to another population. So, and also we have to consider that our young participants never knew a world before tech. Therefore, they were able to jump into VR and know exactly what to do without us even giving them instructions. Of course, there was a demo, but they caught it on pretty quickly. And this is something to consider in terms of what we looked at. And again, all of our participants fell within the measurements and system specifications, which is good, but at the same time, that also is a limitation to these systems. When it comes to our broader impacts, we hope that we improved the immersive experience of training environments, or at least that is the overarching picture of why we went about looking at this study. When it comes to contributions, we contributed subjective and objective data on locomotion in general, locomotion and VR in general, but then we also hopefully expanded the knowledge of state-of-the-art locomotion systems and did a reasonable comparison. In terms of future studies, we would recommend that people look at these systems in terms of how much physical exertion participants have while in these systems and their emotional exertion. We would also recommend anyone wanting to look at these systems in the future to consider these things. One being objective. In other words, what kind of tasks are you having participants do in these systems? Are you having them reach right in front of you, bending over, reaching high? Again, goes back to our system preferences. The cost of these systems, of course, these systems can vary widely in terms of their costs, so that may be something to consider in terms of your budget. Reliability, you may want to consider if these systems will last for 100 participants, 1,000, 1 million, depending on how many you run, or you may just need it for a couple of participants. When it comes to footprint, these systems also, as you saw in our little images, our little videos, that they have varying levels of space required for them, so that may be something to consider. And also preference. Although something may be faster or easier to use, although something may be faster or the data shows that, oh, this is the best system, you also have to consider what users like to use, because sometimes when users prefer to use one system over the other, they will spend more time in it and they'll enjoy themselves in it, therefore causing information to be retained a lot better. So on that note, we'd like to give our thanks and acknowledgments not only to our reviewers, but also to our team who made this possible. So thank you to Jim O'Neill, Liz Scarrett, David Garber, Matt Watkins, Matt Crone, and Aaron Perez. And as well, we hope that this experiment showed you guys a little glimpse into the new VR locomotion systems coming out in the future, and we hope that you guys will also take this as an inspiration to improve infinite and easy-to-use locomotion in VR. Thank you.
All right, we have time for some questions.
No,
Yeah.
not really.
Yeah, no, like I was telling Jim not too long ago, I was expecting to code in Unity and do some VR stuff, but yeah, no, to be able to go out and touch systems that are not everywhere, These systems, of course, cannot be afforded by everyone, and so to be able to work on these state-of-the-art systems and also do an experiment with it in the amount of time that we did with the support of the team that we did, yeah, I was not expecting this for this summer. And it's still not over.
Hey, Daryl and Luke, good job. Great presentation. I had a question. When you were setting up all of these different systems, was there any hiccups or complications that you ran into that you weren't expecting on any of the systems?
Yeah, so for all of the systems, we kind of were fighting with Steam VR. We had a lot of like Steam VR crashing. You know, we mentioned a lot of tracking issues. That was pretty much the bane of our existence. So yeah, that was the main issue. There were also some issues with like the Infinitec desktop software, which I did mention during our support meeting, you know, to give some feedback. But yeah, it was mostly Steam VR issues and, you know, calibration, tracking, things like that. Yep.
Is there a headset? So I know that you used the Vive Pro for the experiment. Is there a headset that you think would be better suited for these types of locomotion systems?
So we think that a lot of the issues that we had with like the tracking and stuff like that could be mitigated if we had inside-out tracking, like with a Quest or something like that. So that would be one thing to consider. Another thing that sort of, I don't want to say messed up, but added maybe unnecessary data was that participants sometimes complained about the headset itself, or like it was slightly too blurry or things like that, that really were not relevant because we weren't evaluating the headset itself, we were trying to evaluate the system. So maybe a headset that had less of those problems might be better.
Yeah, no, that'd be a great future study to look at different headsets on these different systems.
You had two graphs up there that were about the amount of head movement. I'm interested in why you were particularly tracking that when you were talking about locomotion, and also whether you have, is head movement a good or a bad thing, right? Because if I'm feeling uncomfortable, I'm going to be really rigid and not move, whereas if I'm comfortable, maybe I'm looking around more. Or maybe it's, oh, I don't know where I'm going because I'm sliding around, so I have to move around. So I'm curious if you have any observations about both why you did that and what those observations yielded.
Yeah, for sure. So we looked at head movement because we were suspecting that participants may bob their head a little bit more in some systems. And so we were looking to see if head movement was something to be different. If participants move the same distance, because we looked at it in a 3D space, right? If participants move the same distance in a 2D space, of course, there would be no differences. But since we looked at it in a 3D space, we wanted to consider things like head bobbing or weird movements where they're jumping or something. So that's why we took the 3D space in terms of head movement. And I'm sorry, what was your second question?
Well, is it a good or bad thing that they moved or did actually not?
Yeah, no, that just may be the nature of the system. Participants bobbing their head a lot more doesn't necessarily mean that it's a bad thing. But again, this is physical exertion that you're doing, and this, you know, it may be uncomfortable for participants, especially wearing a headset on their head. It may be moving on their head. So it may be a good or it may be a bad thing. That may be the nature of the system. You need to bob your head more to move, but yeah, that was just a measurement that we thought may give us a little bit of insight into these systems.
So were you only looking at up and down movement for bobbing, or were you also taking into account, like, oh, I'm looking around to see where things are?
So we did do head rotation, and we aggregated that for every participant, but we also took the head-mounted display within a 3D space. So therefore, again, like I said, in terms of the XZ direction, participants should have all been the same. Therefore, if we measured XZ, we should have seen no statistical difference, but we measured it in the 3D space. Therefore, with our assumption that participants would move the same in terms of an XZ distance, but again, did they bob their head more? So we looked at it within the 3D space to try to take into account movement in terms of bobbing.
Were there any effects based upon the physical characteristics, like the taller participants had more difficulty or shorter participants were easier or things like that?
No, for sure. So we actually had one participant that was a little too tall for one system and feet were a little too big for another system. So that participant, although they completed most of the tasks, again, the linear mixed effects models that we used took that into account, again, missing or imbalanced data. So therefore, that participant did get to complete some tasks, but not all of them. So we did have one participant not complete tasks in a system or two because of their, not demographics, but their physical attributes. So again, that was something to consider hopefully when you guys look into future VR systems, locomotion systems.
All right, that's our time for this talk. Let's thank our speakers again.